factors will enable us to make a machine that is both faster and more compact and have got less power consumption than the machine that we got out today. And especially we can reduce the number of boards in the system. We can actually deliver one of these instead of two 2 megabyte boards and an ND-100. And in that position where the old memory management used to be, we can in fact put Ethernet or Net1 or token ring, because they are only using the A connector. So it is possible, and on all older systems without the fixed backwiring, to put that in there. On the compact Samsung, this will be provided so that it can be put in there straight away. That's all I got on technology and on the features. So are there any questions before I continue with the cache? I thought I'd do the cache and then we could take a short break, about 10 minutes, and then Chris can continue with the rest of the program here. We are not using 4 hours as we put down initially. The machine is not a lot different from Rask, and we put a lot of the information in the information package that we will not go through in detail. We will tell you how to read it, and you can then go off and read that by yourself. And we don't want to spend a lot of time on technical details at this stage. Any questions? I'll then go on with the cache. It will require some explanation to tell you that this is better than on Rask. On Delilah, we've got only 2 cache banks compared to 4 on the Rask, and we can not claim that this will have a higher hit rate than the Rask. It will have a lower hit rate than the Rask. But it has got several other advantages that I will come to in a minute. One of the advantages is that we will get 1K more space for microcode, because the micro instruction cache is using up the area used for the microcode. And when we reduce the number of instruction cache banks from 2 to 1, then we'll have 1K more microcode space. Also, another feature with the new cache that's got nothing to do with the size of it is that cache clear is now instantaneous. It takes 1 cycle instead of up to 1K cycles on the Rask. If you did 2 cache clears in a row, then you had to wait for up to 1K cycles, 1K non-memory reference cycles, in order to get it cleared. And if you came to a memory reference cycle and it was going to update the cache, then it's just sat there waiting for the cache to be cleared, or for the used bank to be cleared. I'll now go into more detail on the size of the cache. The instruction cache on Delilah, the 2 cache banks we've got is 1 for instructions and 1 for data. That's the 2 major banks. The micro instruction cache can be looked at as an extension of the instruction cache bank. So it's logically 2 1K cache banks. On the Rask, we had 2 instruction cache banks and 2 data cache banks. If all accesses were distributed evenly among these 4 cache banks on the RASC, then we would have reduced the hit rate by a couple of percent, and the miss rate, which is the vice versa, with about that would be twice as high. But the hit rate is perhaps 99% on the RASC, and it will now be 98. If it was 98, then it will be 96%. So the performance decrease won't be a lot. That is if the system was balanced. If for example, the data accesses on the ND-110 CX were distributed 30% APT relative and 70% PT relative, or vice versa, then the benefit of having 2 data cache banks wouldn't be that much, and the decrease in performance on Delilah will not be all that significant. And especially with the instruction cache bank, where we got 1 for the user level, for level 1, 1 bank for the user level, and 1 bank for the others, then that was definitely not balanced, because what was done on the other levels were short bits of code that did not span a 1K area regularly, normally. So that was very, very unbalanced. So you didn't get any performance increase at all with that. Perhaps with a lot of users, maybe it's difficult to measure, but definitely if you got only 1 process running, like running a whetstone performance, you can only get about 0.1 of a kips out of the extra instruction cache. But that's not really a valid argument, because this instruction cache bank is relevant. It's important when you got more users. But I guess we will not have such a dramatic decrease in performance because of this as you would think. Also on the ND-110, we had, when we did a write in one of the cache banks, we had to go through, if you remember from the RASC course, we had to go through and check for hit in the other cache bank, and if we had a hit in the other cache bank, we had to invalidate that used bit. And we also had to go through the 2 instructions cache banks and see if we had a hit there and invalidate it. And so the write cycles actually took about twice as long time as on Delilah, because if we are writing to if we are writing to the cache, and the address that we are writing to is in the instruction cache, that is, we got a hit in the instruction cache on the write, we must invalidate this before writing, of course, only to the data cache. But on the RASC, we had to invalidate 3 banks instead of 1. So that will take just twice as long as on Delilah. So we'll get write cycles with that will be less than half of the RASC. Here's just to summarize this. The buffered write cycles will be twice as fast as on the ND-110 CX. And same as on the ND-110, instruction cache and the micro instruction cache, they're updated on fetch cycles. Data cache is updated on read and write. And it's the write through cache So we're updating both the memory and the cache on a write. But the buffered write will have the feature that the CPU will only write to the cache and start a memory access. It will not wait for it to finish. It can then immediately continue and execute the next instruction if that's found in the cache. And it can then continue for several cycles while the write is progressing, if you got hit on all accesses after that, all reads and fetches. If you got a write, then you got to wait again, of course. This simplification of the cache will also have other benefits. We will only need one set of used bits for the instruction cache and one set for the data cache, which is much more easy to follow than on the ND-110. On the ND-110, you had first of all to have one set of used bits for each cache bank, which will make 4 of them. And in addition, you had to have a spare copy of the whole thing that you were clearing in the background while you were using the current set of 4 used bit banks. But now you don't need that because cache clear is instantaneous. Only one cycle. It's a package with direct clear. And only 1K of micro-instruction cache will free 1K more to microcode use. We've also changed the cache status register format a bit. It's 2 changes there. We've added a bit here, a bit called inhibit. That's bit 4. And that is a 1 if the last write only went to memory. That is, the page was inhibited. The cache was inhibited for write. That's been a feature that a lot of people have wanted for a long time, so that you can actually, in this way, almost read the cache inhibit limit map. That's before this, it's always been writable. That was the easiest way to implement a read from that map without a lot of extra logic. One bit here was introduced on the ND-110. That was CFIN, or cache clear finished. Since cache clear is instantaneous, this will always be a 1 on Delilah. We've also got several other cache status register bits here that are mostly there for historical reasons. The cache on is the switch. The mandis, or manual disable, used to have a different function a long time ago. Now it's just the inverse of the switch. Cache off, same switch but just inverse. And also there is a cache updated bit, which will tell if cache was updated on the last memory reference or not. This is not of very high significance anymore. It was useful on the ND-100, where when you did a cache clear, you did not use the cache after a cache clear was initiated. So you just went on without updating the cache. That was different on the RASC, because on the ND-110, then the machine was halted while cache clear was performed. On the ND-100, the cache was just not updated, but the machine continued, which may have been a better strategy. But all in all, I think we've got a cache here that has got the potential of giving us the same or better performance than the RASC, and it's a lot simpler to understand. You won't get all that many problems early in the product's lifetime. And so I think all in all it's quite a balanced approach. And when it comes to all the other features that we've got on the board, it has been possible mostly to technology, new technology, not a lot of architectural changes, to get a machine that has improved both on performance, on price, and on density of the board, the number of boards. So that will conclude my presentation here. Thank you very much. Any questions? Okay, we'll have a 10-minute break.
Sorry. Yes, yes. Oh, never mind. Okay, right. I'm going to talk to you a little bit about the two parts that are fairly new to the Delilah board, one of which didn't exist on RASC at all. That's the dual-ported memory. And the second of which is the bus interface, which, of course, existed on RASC, but has had to be modified in order to accomplish the dual porting of the memory. So I'm just going to go fairly briefly through this. We'll finish by lunchtime, I hope. Don't want to get drowned out by the sound of rumbling stomachs, so I think we'll try and keep it fairly short. Okay, well, I've been through most of these points already, but let's just reiterate them. Got a dual-ported memory on board, and there are two options that we can insert into the board. We can provide 2 megabytes, that's 1 mega word, or 4 megabytes. They're on 1 meg by 9 SIP strips. The extra 9th bit is for parity. Parity is computed on a byte-wide basis, so we've got 2 parity bits per word. Now, of course, we've got local memory on this board, so we have to keep parity error address and status information both locally for the local memory and for the remote memory as well. So we've had to double up on the parity error address and status words. The memory size obviously is controlled partially by population, how much you put in there to start with, and you have to change a PAL, or actually 2 PALs on the board to tell the board where the memory limits actually lie. It's assumed to start from 0, but its upper limit is controlled by what you actually put inside this PAL. We've put the feature there that you can turn all the memory off, as Lasse has explained, with a switch, so it just ceases to be there. Gives you a slight complication that if you have local memory which you switch off, you then have a hole in memory which you have to switch in from other cards on the ND-100 bus. We've got 2 semaphores in the local memory, one for CPU accesses to the memory and one for bus accesses to the memory. So that merely means that if the CPU had the memory on the last cycle, the bus can't come in and change a location in memory before the CPU's had another chance to access the memory again, and the same from the bus side. The priority scheme that we've got in the memory has been simplified a bit from RASC. We started off with refresh as the highest priority. The other 2 sources of request are, of course, the CPU and the bus. The CPU is given a high priority immediately after a refresh. Otherwise, the bus is allowed the access, and at the lowest priority is the CPU when the last access was not a refresh. So that is the priority in the local memory. If we just look at the overall characteristics of the ND-100 bus interface, Of course, it'll handle all the ND-100 bus signals and timings, just as the RASC bus interface did. It controls the multiplexing of the local BD, which we call LBD. BD is the data, multiplexed data and address on the ND-100, and the local BD is a local version of that. I'll explain a little bit more about the LBD as we go along. There's also a semaphore for the ND-100 bus memory, exactly as on RASC. The ND-100 bus interface also includes the old parity error address and status words for the ND-100 memory, which is loaded with address and status should there be a parity error in the bus memory. The refresh, again, has got the highest priority on the bus arbitration. In fact, the priorities here are identical to the priorities in the memory. Refresh highest, CPU gets access to the bus if the last was a refresh. Otherwise, DMA devices will get the bus whenever they want it. And at the lowest, the CPU can have it when DMA doesn't want it. So that's the overall picture of the ND-100 bus interface. Now, because we've got dual-ported memory, the bus interface and the memory have to work fairly closely together. And the dual porting of the memory is accomplished by multiplexing data on this thing, which is the LBD. This is the local bus data. Here's the ND-100 bus. So we have really three possibilities of data flow between the processor, the bus interface, and the memory. The processor can talk directly to the local memory if it feels like it, without involving the ND-100 bus at all. So that means that while the processor is talking to local memory, the ND-100 bus can be taking traffic between DMA devices and other ND-100 memory, or DMA devices and multiport. So that should give us an increase in performance there, not only by the fact that the processor can talk to a faster memory, not without involving the bus, but also that DMA won't impinge on the processor at all during that period. The second option is, of course, the processor talking to ND-100 bus, multiport or memory on the ND-100 bus. There it does just what the RASC used to do, go through the bus interface via the LBD here and talk to the ND-100 bus. That's the second option. And the final option, of course, is when DMA wants to talk to local memory. It has to go through the bus interface on the LBD here again and talks to memory. Obviously, while that's going on, the processor can't be talking to memory because the ND-100 bus has got it. So those are the three possibilities of data flow within the memory and bus interface. Not sure if this will fit on, but I think we can get most of it. Oh yeah. Good. In slightly more detail, that is the interface between the processor, the bus interface, and the memory. Here's the LBD connecting a buffered version of the cache data, cache address, and physical page number to the LBD. The bus interfaces to the LBD here, and the memory interface is here. When the processor, let's go through the three possibilities of data flow in here. If the processor wants to talk to local memory, the processor is obviously going to put an address out on the cache address and the physical page, which then comes in to the local memory. That's compared with the address range that is held within the PAL in local memory. If it corresponds to an address which is in that local memory, then it'll push a signal over to the bus interface saying the CPU has granted the memory, and the bus interface will switch these buffers on, it'll switch its own buffers off, transfer data and addresses to and from the memory that way. On the other hand, if, in the second case, the processor wants to talk to the ND-100 bus, again, the processor will put the addresses on here. Again, the the high order address bits will be compared at the front end of the memory again, but this time the memory will not respond with a equivalent of a memory hit, if you like. And it will signal the bus interface that, okay, it's a memory access, but it's not my memory. In that case, the bus interface will then start up a bus cycle, an ND-100 bus cycle, in just the same way it did on RASC. And then the data that appears on LVD will be fed through to the ND-100 bus. So that was the second case. The third case is where the DMA wants to talk to the memory. Here, there will be a bus request signal coming off the ND-100 bus. That will then, the address will appear on the ND-100 bus here, sampled with BAPR. That's not shown on here, but it is anyway. That address is again compared, the top order bits of the address is compared within the memory, and it may be a hit or it may not be a hit. If it is a hit, the memory will respond to the bus interface with a B grant, which is the bus grant, so the bus has got the memory, in which case the bus interface will carry out all the necessary multiplexing of address and data through to the memory to provide a channel from the ND-100 bus through into the memory. If the address that's put onto here and sampled with BAPR on the ND-100 bus does not correspond to something in the memory, then there will be no acknowledgement gone through there, and that bus interface will handle that memory access in exactly the same way RASC does. It'll just give the control signals so that data on here will go to an off-board memory card or to multiport. Does everybody understand that? Is that okay? I've probably explained most of this anyway to start with, so it's just makes it a bit clearer perhaps. Out this side is the ND-100 bus. Out at this side is the CPU. This is the data path within the memory and bus interface. So in here we have a set of latches up the front which sample the addresses coming from the CPU, and we have some data transceivers here. The first thing that's done is the address from the CPU is latched there and will be fed onto the local data bus to go either through to the BD if the memory address doesn't correspond to one which is local. If it does, it'll go over to the memory there. Later on, the bus interface will switch the data transceivers on in one or other directions, depending on whether it's a read or a write, to send the data through to the BD or off to the local memory. We have the parity error address status registers here, which are the old ones, attached directly to the BD, so that even if the local memory isn't getting involved in a data access, this will still latch parity errors which took place on the ND-100 bus. If we look at the block diagram of the memory, I'll have to shift it over a bit halfway through. At the front end of the memory we have this address decoder which is looking at the bus address and looking at the CPU address. It's sampled, the bus address is sampled with BAPR and the CPU address is sampled with a signal called ECREQ. So this is then comparing those two addresses with its address range. It knows it starts from 0, but the upper limit, as I say, is programmed into 2 PALs. If there's a hit, it'll push forward to the arbiter either a bus local memory request signal or a CPU local memory request signal. If not, it pushes out a signal to the bus interface which says, right, you handle it for the ND-100 bus. The arbitration then takes over and arbitrates between the 3 sources of request for the local memory. One is refresh, the other is the bus, and the third is the CPU. And it will push out a grant signal for whichever of those is successful. Once it's decided what sort of cycle it wants to do, for whom it wants to do it, it'll start up just a standard memory cycle and start up a control sequencer here, which is labeled RAM control. That then initiates a dynamic RAM cycle. It controls the RAM, it controls the multiplexing of addresses from the LBD to the RAM, and it will also control the data flow to and from the RAM through two parity latches. So the data comes through here, the parity is computed, compared on a read, or computed and written into the RAM on a write. The data is then gated onto the LBD under the control of this. If there's a parity error, it comes out here, and that is then sent to the bus interface. So that's a block diagram of the memory. Are there any questions on that one? Block diagram of the bus interface. There are two main sections in the bus interface. One is concerned with the data path, which we saw a few moments ago. That handles the switching from LBD, PPN through to address. And then the other section is mainly concerned with control. There's the arbitration scheme, which is in a PAL, so that can be changed if we need to. So this takes in two signals, refresh, CPU request, and actually the bus request comes in from the ND-100 bus. We have a bus cycle control which handles the sequencing of the various signals for the ND-100 bus, and we have a parity control here which handles the loading of the parity error address and status registers should there be a parity error. And then of course there's the ND-100 bus drivers. So really there isn't very much more there than there was in the RASC. Whoops. Than there was in the RASC. It's just got a bit more complicated. So really that is it. Things haven't got a lot different. The memory is extra, and the bus interface has got a little bit more complicated. I don't think there are any great difficulties there from anybody's point of view. Let's just go through this information package that we've given you. This is what's contained in the information package. There's a brief explanation of what switches and indicators there are on board. We've got a load of straps, of course, test points. Well, you can read that yourselves, can't you? You can read it to you. Those are the switches and indicators. As on RASC, we have a cache on, cache off indicator. There's a switch on there which you can turn cache on and off with. That's the same as RASC. And the second switch here is the one to turn the local memory off. At the moment we don't have an LED on that, which is probably an oversight on our part. I think we've probably put one in to make it pretty obvious that we've got local memory turned off. These are the LEDs here. That corresponds to the position of that switch, so it'll illuminate if you've got cache switched off. You've got the usual red and green lights to say the CPU's stopped and running. We've got two extra ones here which will blink, really, if there's a parity error, until the parity error is cleared down in the parity error latches. So we have, if we have a parity error in local memory, one or other, or maybe both, of those will light up and stay lit until that is cleared down. This one shows that local memory is being granted to the CPU, and this one shows that local memory is being granted to the ND-100 bus. That only lasts for the period of the B grant or C grant signals that you saw in the bus interface. So it will be a very rapid flicker. But normally you'll be getting lots and lots of activity on both of them anyway, so they should, in normal running circumstances, both be lit. If one of them doesn't light, then there's probably something wrong somewhere. So those are the switches and indicators. Provided some indication of the various strap fields that we've got here. For the tracer on the ND-100, we've now provided a strap to switch the CD and the IDB through to the tracer data. So you can look at one or the other depending on whether you've got the strap put in or not. We've got the usual ND-100 hardware configuration strap field, which is similar to RASC, just with different values here. So you've probably seen all this before. It's bog standard stuff. Print version, well, we'll define that when we know what the initial print version released for production is. We've got some extra straps which I'll talk about. It's to test the CGA, that's the CPU gate array, the ND-Delilah gate array that Lasse talked about. And in addition, we have another strap which either enables or disables all traps in the system. That could be useful for diagnostic purposes. Test points, we have a few test points which are mainly involved with the internal workings of the CPU gate array. We have signals coming out from the gate array now which used to be derived off the gate array, of course, in PALs, interrupt request, and this wonderful CGA multiplexer. Now, because we've taken a lot of stuff inside the gate array, a lot has disappeared that you used to be able to look at before. It's now inside and doesn't come out on pins. So it's rather more difficult to monitor the internal states of what's going on the board. So to help that, we've dedicated 5 pins on the gate array which are brought out to test points, which bring out various internal states within the gate array. You can control via 3 strap fields, 13, 14 and 15, which of these signals will appear on these various test points. You have the trap vectors. You've got a deep thing which is inside the stack control bits, various ALU conditions coming out, and they're all shown on the circuit diagrams. So using these various strap fields, you can control what comes out on the test points within the gate array. That could be useful. Probably will be. IDB sources. Okay, this is pretty self-explanatory. A few things have changed slightly, but I don't think there are any really great surprises there. You can read that as well as I can. We've provided some sheets on the command decoding. You've seen most of this sort of thing before on RASC. Again, the commands haven't changed much. There are a couple of extra ones that I'll show you a little later on. This is to do with cycle control. It tells you which cycles are slow and which are short. We have various decodes here. Read type, data type, those will encode the 3 or 4 different types of access that can be made. It tells you whether a particular access to memory is read or whether it's data. If it's data, then it means it's either a read or a write to memory. If it's not a data type, it means it's a fetch. If it's a RT, it means it's a read or a fetch. If it's not an RT, it means it's a write. So you can encode your various different types of accesses into those 2. Then we have decodes for write, fetch or map, and memory request. These are just for information internal to the gate array. If we flip over the next one and go to sheet number 8, a couple of extra things here. There is, which one is it? There's MACL and X slow. Is that it's hard to, yeah. MACL and X slow, those are 2 new commands that have been provided. Lasse was talking about the extra command that was produced to load the control store. And X slow will force a very slow cycle. Not sure how useful this will be to you, but it's quite interesting nevertheless. These are the various types of mode that the logical address selection can be switched into on Delilah. Certain things from Rask have been taken out, modes which were dedicated to Syntran 4, they've been taken out. So this has been much simplified. So you've got the various modes if you're in shadow, non-shadow, and where the various logical addresses will come from, how those addresses will be computed. So that table tells you all of that. And finally, there is the trap system, which is again changed slightly. We've added 2 extra traps here, F-trap and V-trap. Those are really for future expansion purposes. Otherwise, it's pretty much the same as Rask is, except that we've taken Syntran 4 traps out, which explains why these priorities just don't go up contiguously. So this explains how a particular trap is produced. For example, if we look at this one, I'll read them out. The page fault, write protect violation, indirect protect violation, fetch protect violation, read protect violation, ring violation, written in page, page used, read, ring down, sorry. F-trap, which is a spare trap, which will only be active on a fetch. It'll only be true if the trap itself is false. You can feed into the gate array a signal which will cause a trap on a fetch. Where's that gone? There's fetch. You'll get a trap there, and it will vector off to that address. V-trap is the same, but on any virtual access that can happen. And then, of course, there's the panel and MAC traps there. So that explains the trap system. That is all inside the big gate array these days, so it's pretty fixed. Okay, I think that's just about it, really. That was pretty quick. Yes. Well, we can talk about circuit diagrams if you like. They're all pushed in the back of the information folder there. They've been produced on DAISY and therefore hierarchical. Presumably you've all seen DAISY circuit diagrams before. I hope. So I don't think there's a great deal to talk about on those. Are there any questions? Anything you want to say, last?
Well, the circuit diagrams are about 49 pages there, and it's done in a hierarchical way, as Chris has said. We have not included the gate array schematic diagrams. Those will probably be in a manual later on, and those of you that will be working on the Delilah will get those schematic diagrams when they're needed. They're about, for the big gate array, it's more than 100 pages, isn't it? Yeah. And the small one, about 15 or 20 pages. So it's quite a big design. Although the board is not all that dense. Okay, thank you very much for attending the course. Thank you.